Hello everyone, so today I'm going to show you the result of a study where we try to compare two approaches for transcranial simulation. The first approach is ray tracing, the one that Insightec developed in their device. Insightec is the manufacturer of the clinical device for transcranial therapy, and the other approach is the approach of our lab using K-wave. So a few reminders about transcranial focusing with multi-elements array. So if you have a multi-elements array and elements sonicate in phase, you have a sharp focus in the pressure field. However, when you introduce a skull between the probe and the target, the skull is aberrating and you have a defocused pressure field at target. You are not able to treat the region. The idea is to compensate the effect of the skull by estimating the aberrating effect of the skull in order to, after passing through the skull, restore some pressure and treat the desired brain region. It's very important to estimate as much as you can, as best as you can, the phase shift here, because it will impact the pressure at focused, and it will impact the temperature rise and the treatment efficiency, because the temperature rise is proportional to the pressure to the square. So the idea is to compare here two numerical approaches. One is the K-wave pseudospectral that we use in the lab, and the other one is ray tracing. So both start from the same inputs, a CT, a probe, and a target, and a modeling of the acoustic properties of the skull based on the CT. On the K-wave side, you solve the wave equation using K-wave, and you compute the phase shift at the probe level. On the Insightec side, we don't know the details of their ray tracing algorithm, but we know the principle. And what we were able to do thanks to the software of Insightec is that for any CT and any position of the probe with respect to the CT, be able to extract the phase shift that would be applied at the probe level during the clinical treatment. And then we were wondering, okay, so now how do we compare those phase shifts in terms of focusing quality and restored pressure? To do this, we acquire transfer matrices. So this is the experimental part of the job. To acquire transfer matrices, you basically put the skulls you were running the simulations on in front of the probe, and you scan a volume around the focus with an hydrophone. When you are at a specific point in the volume that you scan, you make elements sonicate one after another, and for each element, you measure the contribution to the pressure field in terms of amplitude and phase. You move to the next point and you redo the same, and you end up with a big transfer matrix that you can use to, for any sets of phase shift, you can reconstruct the pressure field that you would obtain. So the first question we had from Insightec is this valid? Is this approach valid? So what we did is that for a few sets of correction and a few skulls, we actually compared what we were obtaining with the transfer matrix with what we were measuring with an hydrophone while shooting with those corrections, specific corrections applied. And what we showed is that it's actually very accurate. We're able to have an error that's less than 1% in pressure amplitude and less than 0.2 millimeter in terms of peak pressure position. So after validating this approach, we could look at the performance of both Insightec and K-wave correction. And we showed that there is a slight improvement using K-wave going from 83.9% to 85.6% with our correction. It's interesting to say that this result is in line with the previous result that we published using the same algorithm but on a different probe, different geometry, and different number of elements. And what's more surprising is that we were expecting a much lower performance for Insightec, because in theory, when you do ray tracing, you don't model as much, you don't capture as much information as in K-wave in the bone, because you don't have this density and speed of sound modeling that you take into account in K-wave. So this is interesting to say. And to finish, we were wondering if the fact that both algorithms neglect shear waves is impacting their performance. So to answer this question, we look at the incident angles at the skull surface, and we try to compute the performance of both algorithms depending on the incident angles. And what we show here is that for angles above 20 degrees, we have a drop in performance which goes below 75%. So what we see here is that it kind of confirms the fact that we are neglecting shear wave is impacting the performance, because we know that shear wave starts to play a significant role above 20 degrees in the propagation of ultrasound inside the skull. So thank you for your attention. I will be happy to answer your questions if you have any. And also we would like to thank Insightec for their support in this study. Thank you very much.